For decades, buying software was a static transaction. You purchased a license, downloaded an app, and installed it on your hard drive. You owned the hammer, and you could swing it as many times as you wanted without paying a cent extra. But with generative AI, you don't own the hammer. You are essentially renting time on a sprawling supercomputer housed in a distant data center. And because you are renting raw processing power, the industry has adopted a pricing model that resembles a digital arcade. Instead of a flat monthly fee, you pay in tokens, which are roughly equivalent to pieces of individual words. Every time you ask the system to calculate an answer, you have to drop tokens into the slot. If you want the system to draft a simple 3-sentence email, that costs 1 or 2 tokens. It is incredibly cheap and fast. But if you ask the machine to ingest a 200-page legal contract, cross-reference its clauses with historical case law, and analyze the risk, you are asking the system to lift a massive computational weight. That single request might cost you hundreds of tokens. The depth of the answers you can extract from these systems is entirely dictated by the raw computational expense you are willing to incur. In this environment, intelligence is directly tethered to your operational budget. To manage this variable weight, the industry offers different tiers of access. Free public models are like riding a crowded city bus. The company subsidizes the tokens, but you wait in traffic. Premium tiers are like hiring a private chauffeur, offering priority speed and what developers call massive contact windows, allowing the AI to remember thousands of details over a long conversation. And then there are enterprise fleets, completely isolated and heavily armored systems, built so corporate data never leaks into the public domain. This chart graphs the math behind those premium massive context windows. On the x-axis, we have the size of the document you feed the AI, and on the y-axis, the computational cost. Notice how the relationship isn't linear. If you double the amount of information you put into the system, the cost doesn't double, it quadruples. Because of the attention mechanism, the AI has to weigh every single new word against every other word in that giant document to understand the context. As the internal calculations skyrocket, so does the price. Pushing the limits of these colossal models with massive datasets can actually cost a user hundreds of dollars for a single complex prompt. Centralized architecture hits a severe mathematical limit. Trying to run an entire global economy on massive models that scale quadratically in cost is mathematically unsustainable for daily, continuous enterprise work. To escape these ballooning costs, developers are actively migrating away from 100 billion parameter behemoths housed in centralized clouds. Instead, they are downloading lean, open-source models in the 1 to 9 billion parameter range. Because these smaller models require a fraction of the power, they can run locally on your laptop or a company's internal server rack. This shifts compute to the edge, offering zero latency and absolute data privacy. But running a tiny 8 billion parameter model on a local device creates a severe capability gap. Small models lack the sprawling, omniscient knowledge of a giant data center. If you ask a lean model a hard question, it will make mistakes. AI pioneer Andrew Ng recently detailed a massive operational critique of how we judge these smaller systems. He argues the problem isn't necessarily the size of the model, but a structural flaw in how we ask questions, a habit he calls zero-shot prompting. Zero-shot prompting means you type a request, hit enter, and expect a perfectly reasoned, perfectly formatted answer on the very first try. It is the equivalent of demanding a human author sit down at a keyboard and type a heavily researched essay from start to finish without a single draft, without an outline, and with the backspace key physically removed from the keyboard. No human works that way, yet we demand it from digital neural networks. When a small edge model fails under these conditions, it is failing because of the strict single-guess format we force it into. Ng's research shows that if you abandon zero-shot prompting and wrap a cheap model in an agentic workflow, the quality of its output skyrockets. You stop demanding an instant answer and instead give the model a multi-step process. Write a draft, run a test, read the error logs, reflect on the failure, and rewrite the code. We can see this outcome clearly in this bar chart tracking the human eval coding benchmark. When asked to write code using a standard zero-shot prompt, an older, smaller model, GPT 3.5, scored a 48%. The massive, highly advanced GPT-4 model scored 67%. But when that exact same small model was allowed to iterate through an agentic workflow, drafting and revising its own work, it actually beat the massive model's score. You might assume that looping a small model 15 times burns through too many arcade tokens, negating the cost savings. But the generation speed of small models is so incredibly fast, and their token cost is so astonishingly low, sometimes fractions of a penny, that you can afford high iteration. It is the economic equivalent of paying an intern minimum wage to write 15 drafts instead of paying a premium consultant $1,000 an hour to write it once. The intern's 15th draft is often better, and the final invoice is still vastly cheaper. To manage these intern-like loops, developers use underlying architectures like the React paradigm. React forces the AI into a strict think, act, observe cycle. It thinks about where a termination date might be in a contract, writes a script to act on that thought, observes the error logs if the script fails, and then thinks of a new search term. Giving inexpensive edge models the architectural freedom to draft, critique, and revise themselves entirely sidesteps the massive token costs of centralized supercomputers. A single iterating agent represents the first step toward a digital organization, an entire workforce of specialized AI roles working in parallel. No human builds a skyscraper alone. You need an architect, engineer, foreman, and an electrician. This same logic now applies to software development. Take the open-source project ChatDev. You configure distinct personas, assigning one AI as the CEO, another as a developer, and another as a QA tester. You give the CEO a prompt, and then sit back. The CEO delegates design, the developer writes code, and the tester finds bugs. They collaborate, argue over best practices, and refine a finished application entirely in the background. Take a look at this flowchart, illustrating how enterprises deploy specialized roles. It works exactly like a medical triage system in an emergency room. When you submit a contract query, a small, incredibly cheap classifier agent acts as the triage nurse, routing simple queries directly to completion without burning unnecessary tokens. Only when it detects a highly dense, complicated legal clause does it escalate that specific text to an expensive, specialized research agent. But an autonomous workforce carries a critical vulnerability. If a developer agent and a security agent disagree on a piece of code, they can spiral into an infinite loop, arguing for days and burning millions of tokens. To prevent this, companies implement strict governance. They force agents to map out step-by-step blueprints before they act, and they install hard circuit breakers, like a maximum threshold of 5 iterations before the loop halts and pings a human supervisor to intervene. Deploying these systems effectively means you stop focusing entirely on raw compute power and start focusing on rigid structural oversight. Right now, the largest tech companies on Earth are pouring billions into building centralized, monolithic models, betting their futures on housing all human intelligence inside highly expensive, highly guarded server rooms. The quadratic costs of massive models favor this future of local, networked agents. Harnessing this power requires a shift in mindset. You stop treating the interface like a vending machine for answers and start managing it like a dashboard for an autonomous workforce. The ultimate winners of the next tech decade will be those who master the orchestration, governance, and economics of decentralized, autonomous swarms.